Hi, Chris Good here. We're going to do Factorial ANOVA in SPSS, and this is an example that we'll review in class on Thursday, November 6th, and this is the example from the Chapter 13 text. It's just the one that Field works through using these goggles data. This is the same beer goggles study that we've been talking about in class as an example of the factorial design. And to do the ANOVA, you choose the general linear model, the univariate one, from the Analyze menu. So once you click on that, you can, oh, I already did it. Let's move these back where they were. So this is what you're going to see when you open this up for this data file. The dependent variable is the attractiveness of the date. Remember, that says rated by a judge based on a picture the next day. We're going to drag that into the dependent variable box. And then we have two fixed factors, two grouping variables that we're going to use. Let's note that in the data file, they're coded as female and male, none, 2, and 4 pints for alcohol, and each participant gets coded for gender and for alcohol. So we have female none 2, 4 pints, male none 2, and 4 pints, and these are the attractiveness ratings for each of those individuals in this independent group's design. Alright, so we're going to adjust a couple of the parameters here using these dialog boxes, and the first one is the contrasts. It defaults to not doing any univariate contrasts in this case, and so you can see that for the gender factor, no contrast is selected. There's only 2 levels of gender, so we don't really need to do a contrast. If there's a significant effect, we'll be able to see it just by looking at the value of the means. We can determine the nature of the effect. If there's an effect of alcohol, we won't know where that effect lies without doing some kind of a priori contrast. We're actually also going to do some post hoc testing to confirm the nature of any significant main effects of alcohol that we find. We could do any kind of contrast that you want. We could do a simple contrast that compares each level of alcohol to some reference level. So we could compare 1 versus none, 2 pints versus none, or 4 pints versus none. That's not an orthogonal contrast though. Helmer contrast will take the first category and compare it against all remaining ones, then the next category and compare against all remaining ones. So if we did this, if we chose Helmer, and this is very confusing, but once you choose the contrast, you have to hit the change button, and that changes the contrast that you do for the factor that you've selected in the window above. That's, somebody designed it like that. Anyway, when we choose Helmer, what this will do is for both men and women, it will compare no alcohol versus some alcohol. That's 2 and 4 pints together in a chunk of variance in the first contrast. The second contrast will compare 2 versus 4. This will tell us exactly what we want. Does some alcohol affect your the attractiveness rating? And then, is there a difference between the doses of alcohol? That's a contrast that makes sense. I'm going to hit continue. Alright, plots will generate graphs for you, line graphs that, so we want separate lines for gender, and we want alcohol, this 3-level factor on the horizontal axis. Now, once you've selected those, you have to hit the add button to get it into the profile plots dialog box, and then you can hit continue. Couldn't be simpler. Well, maybe it could. Post hoc tests. If you select gender for a post hoc test, it's not going to do them. SPSS will refuse to do post hoc tests on factors with only 2 levels. You should be able to look at the means and see the nature of any main effects there. But you won't be able to see the nature of any interaction, and we're going to come back to that in a second. Alright, so we do want to do post hoc tests for alcohol. I'm going to choose the one that Field chose, the Bonferroni and the Reg WQ. These are going to be presented slightly differently. So let's take a look at what they look like in the output file. So we're doing post hoc tests for alcohol only because that's the only one with more than 2 levels. And we'll hit continue. Finally, in the options box, we're going to look at the estimated marginal means for gender and alcohol and the interaction. I'm going to leave this box unchecked for right now, but here's where you can also put homogeneity tests, descriptive statistics. I might as well click on an estimate of effect size, and we'll hit continue. I'm going to leave bootstrapping alone for right now and hit OK to check out what we've got so far. All right. So as usual, SPSS tells you what it did. It did a univariate analysis of variance with 2 between subjects factors, 2 levels of the gender factor, 3 levels of the alcohol consumption factor, and then we asked for descriptive stats. We got them. These are the means for the men, the means for the women, the averages across gender for each dose of alcohol. Here's the results of our Levine's test. There's no significant difference. This is an assumption of the factorial ANOVA with independent groups. So it's good that we've met that assumption here. No significant differences among the 6 groups in terms of error variance. And here's the meat and potatoes of this whole analysis. These are the tests of between subjects effects, and after the model and intercept sources of variability for the sums of squares, we can see sum of squares for the main effect of our A factor, gender, the main effect of the B factor, alcohol, and the interaction term. Then we've got error and total sums of squares, degrees of freedom, and variance. Let's take a look at the main effect of gender. Here's the sum of squares. We had 2 levels, so 1 degree of freedom. That makes sense. Here's the variance, and the F ratio divides the variance for the A factor by our error variance, our residual variance, our within treatments variance. This is small and not significant. Here's the effect size, the partial eta squared, also pretty small. No significant difference between men and women on average. Here's the effect of alcohol, right? Sum of squares. We had 3 levels of alcohol, so 2 degrees of freedom there. Here's the variance. Divide that by this number, the error variance, and you get a big value for F. That is significant. So we have a significant difference somewhere among the 3 alcohol conditions when you average across gender. Finally, the interaction. Here's what's left over from the model. You should find that this number and this number and this number together add up to the corrected model sums of squares. And that interaction had 2 degrees of freedom left after taking out from the 5 model degrees of freedom, 1 for gender, 2 for alcohol, 2 left over for the interaction. Here's the variance. Divide that number by this to get F, and that's significant as well. So we have a significant interaction, and we're going to have to find out what the nature of that interaction is. Here are the results of the contrast, comparing level 1 versus later. So level 1 of alcohol, right, was 0 pints versus some alcohol. Here's the p-value right here, so significant. Some alcohol, if we go back to the means up here, some alcohol, right, looks like it's giving you lower attractiveness than no alcohol. So if you look at sort of the midpoint between these 2 means, it's lower than this mean up here. The second level is level 2 versus 3, 2 pints versus 4 pints, and according to the contrast, that's significant as well. So that's giving us some answers in terms of the main effect of alcohol. Hasn't shown us what the interaction reveals yet. Remember, because this interaction is significant, we can't really talk about what this main effect of alcohol means. So, well, you're going to have to leave these custom hypothesis tests behind. Let's see. So further down, we get to the means for men and women. This wasn't significant, remember. The means across the levels of alcohol consumption, this was significant. And here's the gender by alcohol consumption. Now, the confidence intervals you see here have not been corrected for multiple comparisons. So we can't really use these definitively as saying, oh look, for men this rating 35 is outside the lower bound of the confidence intervals around the none and 2 pints means, so that difference must be significant. That hasn't been corrected for multiple comparisons. Similarly, this female mean here is within the bound here of both of these, but we still can't say that that's not a significant difference either. We could look at post-hoc tests, but remember, that's only going to tell us about alcohol at none versus 2 versus 4 averaging across gender. We still haven't been able to get at the true nature of this interaction. I told you that the Reg WQ would look a little bit different, and it does. So this is the type of post-hoc test that creates homogeneous subsets that is looking for means that are not significantly different from each other. So the mean at 4 pints, there is no other mean that is not significantly different from that, and so this mean itself constitutes a subset. There's no p-value that makes sense. The p-value is 1 because it's the only one in here, and so to compare it with itself gives you a p-value of 1. The none and 2 pints groups sort together though, so they constitute themselves a homogeneous subset, meaning that these means are not significantly different from each other, and here's the p-value to show it. All right, so this is not a significant difference. So that means we've got 2 groups here. It means that the 4 pints group had significantly lower attractiveness rating than the 2 and the 0 pints groups when taken together as a whole. All right. The plot actually gives us some information. It looks like that women are pretty consistent and then men go down at 4 pints, but we don't have any numbers to back it up, and we're out of analysis at this point. Now on page 531, we have our first glimpse into running syntax in SPSS, and this is how to do a simple effects analysis, and this is the way that you can get at that interaction. So to run syntax, you actually have to create a new document, new syntax document, and you can type in the code. It's just 2 lines. It's actually not that challenging on page 531 of fields text, and it goes like this. Run GLM on the attractiveness variable by gender and alcohol. So that essentially is saying do the factorial analysis of variance with these 2 fixed factors and specifying the dV. The next is the estimated marginal means will come out as tables for the gender, oops, that should be a parenthesis, sorry, for the gender by alcohol interaction. All right, and we'll compare those levels of alcohol by the gender factor. All right, so if you select all of this and hit the big play button, it will run the syntax and generate output that goes directly into your output file. So you can find this again on page 531. And this generates estimated marginal means for the alcohol levels, but split by gender. It also gives you pairwise comparisons between men and women at each level of the other factor, and gives you a p-value that essentially has been adjusted for multiple comparisons. It says that it's equivalent to no adjustments, but there's some debate as to how stringent this is, but acceptable in some circles to go ahead and rely on these estimated marginal means as post-hoc comparisons. So men versus women at 0 pints, not significant, right? And it repeats the analysis going the other way. So men versus women and women versus men, the numbers are the same, but the mean difference is backwards. At 2 pints, men versus women, not significant, right? And same deal if you do it the other way around. Here's the only significant difference. At 4 pints, men have a significantly lower attractiveness rating of their dates. There's your p-value, and it shows the confidence intervals as well. And there it is. There's our estimated marginal means in terms of the simple effects analysis that we ran in our first syntax that we programmed in the SPSS. That's it for Factorial ANOVA, and we will see you next time.